Hello everyone. Today it's my pleasure to be here to present our work with the title Mining and Exploiting Mobile Payment Credential Leaks in the Wild. I'm Shang Chenshi and we are researchers from the Chinese University of Hong Kong. My talk will be organized as follows. First, I will give a brief introduction to the third-party payment service for mobile apps, including the involved parties and its general workflow. Next, I will talk about the credentials used in mobile payments, which will help you to better understand the exploits discussed later. After that, I will introduce the possible leaking sources of payment credentials, as well as the potential exploits with the leaked payment credentials. Then I will present our automatic tool to discover the payment credentials leaked in the wild. Also, I will discuss how to identify the leaking merchant apps from their credentials. Finally, I will give some suggestions for fixing the payment credential leak issue to conclude this talk. So first, let's talk about what is third-party mobile payment service. In mobile payments, there are three parties involved, namely the cashier, the merchant, and the user. Notably, the cashier and merchant here stand for their backend servers, while the user is represented by the cashier app and merchant app installed on his smartphone. The target of the mobile payment protocol is for the user to pay the merchant app through the cashier. So first, the user needs to log into the merchant app in step 1, which can be conducted through the single sign-on service that may be provided by the same service provider or cashier. After the user shops and choose to check out with the third-party cashier, the merchant app generates an order request to its server in step 2. Then, the merchant server will respond with a payment order in step 3, which contains app information and other order information. The app information here includes an important parameter called notify URL, and we will use it later. Then the merchant app forwards the payment order to the cashier app in step 4, while the cashier app will present the payment details, such as the total amount to the user for authorization. Once the user authorizes the payment, the cashier will generate a payment request to its server, or just the cashier server in step 5. After processing the payment, the cashier server will send 2 types of instant payment notifications to the merchant, namely the synchronous notification and asynchronous notification. The synchronous notification, or step 6A, is the immediate response to the payment request, which goes through the user device in step 7 and arrives at the merchant server in step 8. In contrast, the synchronous notification, or step 6B, is sent to the merchant server from the cashier server directly, according to the notify URL specified in the payment order in step 3. Also, the cashiers usually provide other management interfaces to their merchants, which can operate on the cash account of the merchant app. For example, the merchant server may send requests to the cashier server directly in step 9 to perform some transactions, such as refunding the paid orders. Then, let's talk about the credentials used in mobile payments. In the workflow below, almost all the payment-related messages, except for step 2, are protected cryptographically. Since there is no unifying standard for mobile payment, the cashiers all define their own credentials. In this work, we studied the credential leak issue for four first-tier third-party cashiers. These cashiers serve over 1 billion end users globally. However, according to the requests from these cashiers after our responsible disclosure, we will not release their names and just use cashier 1 to cashier 4 to donate them in the following slides. So the payment credentials can be categorized into 2 types. And the first type is the payment key, which is used to generate the digital signature or HMAC. Then the merchant can choose either method to protect the payment messenger. Meanwhile, none of the studied cashiers require the encryption on the payment messenger so that these messages becomes readable to the normal user or even the attacker. On the other hand, the security setting of payment keys are different across the cashiers. For example, some cashiers will generate the key and assign it to their merchants, which is instead user-defined in the other cases. In the case of digital signatures, both the merchant and the cashier need to maintain a pair of asymmetric keys and share their public keys to validate the incoming messages. However, the public key of the cashier tends to be global across the merchant apps. These security settings can cause some security issues, and I will talk about the corresponding drawback later. Apart from the payment keys, there are 2 other credentials defined by the cashiers in order to provide better security. The first one is the Android signing key. When the cashier's app receives the payment order in step 4, cashier 2 and cashier 4 will authenticate their merchant app by checking its package signature against a pre-registered value. Thus, the merchants must keep the associated Android signing keys private. Also, cashier 2 issues client certificates to their merchants, which are used for separate authentication on the network layer in the management interfaces in step 9. For example, refunding the paid orders. In such requests, the merchant server needs to present its client certificate to the cashier server to authenticate itself. Now let's discuss where the payment credentials can be leaked in the wild. In summary, there are 3 potential leaking sources, and I will go through them one by one. The first leaking source is the public Git repositories such as GitHub. Such leaks in GitHub has been known before and have been studied by many previous works. Despite this known finding, we also find some websites which set up their own GitHub service on public IP addresses and make their repositories public, which may also contain the active payment credentials. The second leaking source is mobile apps. Because many app developers may deploy the server-side projects in the front end, in this work, we mainly focus on the Android apps because their installation packages or APKs can be easily obtained from the third-party app market. Also, in our preliminary study, we find some credentials already exist in old mobile app versions, meaning these app developers have tried to hide the leak issue by pushing new versions. of mobile apps. However, the leaked credentials are still valid and can be uncovered by the attacker. Out of our expectation, we find the merchant server can be another leaking source, which has not been studied before. Such leaks are caused by two major reasons, namely the flawed backend SDKs from the caches and the insecure access control setting by the merchant in its server. Here we give a concrete example for better illustration. The figure here shows the structure of a flawed SDK. To be specific, the scrapped file notify_url.php is responsible for processing the asynchronous notification mentioned above. Meanwhile, the configuration file, namely payment_config.php, sets the payment key to a static file. In other words, private key.pem. What's still, this SDK does not restrict the access to this static key file by default. As such, the attacker may guess the URL endpoint of the credential file based on the value of notified URL, as well as the SDK structure. Then the attacker can steal the payment credential file directly if the merchant server does not forbid the access to it. Then I will present 4 types of exploits enabled by the leaked payment credentials. As we will see, these leaked payment credentials can affect other innocent merchant apps without leaks or even another third-party service for mobile apps. So first, with the leaked payment credentials, the attacker may impersonate the benign merchant and forge requests to the cache server for some critical operations, which include downloading transaction records and refunding paid orders. In some cases, the attacker may even steal money from the merchant's cash account by crafting a money transferring request. Even if, remember that Credential 2 requires the client certificate in these management interfaces. We have detected over 3,000 leaked client certificates, which enabled merchant implementation attack. Such an exploit will cause both privacy violation and financial loss to the merchant apps as well as their end users. On the other hand, some careless app developers push their own front-end code online, which includes their private Android signing keys. As a result, the attacker can change several lines of code in the original code base and repackage a malicious merchant app. By replacing the payment order in step 4, the victim user can be tricked into paying for the attacker's order. Overall, we have detected over 400 valid Android signing keys, and 10 of the related Android apps have over 1 million downloads. The third type of exploit is related to the single sign-on service. Actually, some caches also provide third-party authentication service through single sign-on. In other words, some mobile apps can integrate the single sign-on and payment service from the same service provider. However, these caches may not separate payment and single sign-on, these two services properly, which may share the same set of user IDs, enabling the so-called profile exploit in single sign-on. In profile exploit, the merchant server trusts the user ID from the user device by wrong, but miss the token request to the service provider or cashier. As a result, the attacker may modify the value of user ID in his device to steal the victim's account. Although the cashiers usually set the user ID to be private, the attacker can use the leaked payment credential to launch the implementation attack and get the user IDs of all paying users from the related transaction records. Consequently, the attacker can hijack the original accounts of victim users in the merchant apps. Besides, we find that some developers reuse the values of their payment keys to be the single sign-on secret, which amplifies the impact of payment credential leaks to single sign-on. According to our test, 2% of the payment keys also work as the single sign-on secret. The fourth type of exploit is so-called cross-app notification forgery, which enables the attacker to cheat other innocent merchant apps that do not leak their credentials. As I mentioned above, the cashier's public key tends to be shared across the merchant app in the case of digital signature. Thus, the attacker may treat the cashier server as the signing oracle and control the value of notified URL in his crafted payment order to forge some cryptographically correct payment notifications. Then, he may send these forged messages to the victim merchants. Once the merchant server overlooks the app identifier inside, such as the parameter merchant in the given example, it will be cheated and enable the attacker to shop for free. Then I will present our automatic tool to discover the payment credentials leaked in the wild, as well as the empirical testing results. In short, we developed a tool called PayKeyMiner to enable the large-scale mining for payment credential leaked in the public Git repositories, Android APKs, and merchant servers. The tool is made up of 3 modules, namely crawler, scanner, and detector, and I will go through them one by one in the following slides. So, the crawler will first identify the payment-related Git repositories with the help of GitHub search API and 4 search engines, including Google. Towards this end, we summarize 3 types of environment in the integration of mobile payment to construct the cashier-specific query streams. Such environment can be either data, code, or file name. For example, the public key of cashier 3 is global and shared among its merchant apps. So we construct the segment of its public key as one of our query streams. As to the Android apps, we collect APKs in various versions from third-party app market to set up a full-scale database, because some leaked credentials may only exist in old versions. The tool will then process these APKs to check whether they use the third-party payment function. Here, our tool relies on 2 heuristics. First, the merchant app must use the official front-end SDK to send the payment order in step 4. Also, the cashier always requires the merchants to register certain activities in Android manifest.xml to receive the synchronous notification in step 7. The table below shows the screening result, where overall 1 million APKs have been tested by our PayKeyMiner. Among the 4 studied cashiers, Cashier 2 is the most popular and used by almost 1/5 of the test app. The second module in PayKeyMiner is called scanner, which recognized all potential payment credentials from the crawler output to a given GET repository or Android APK. The tool will perform white box scanning because we can check their code directly. To be specific, the tool will trace back the history first because some leaks only occur in old versions. Then our tool can get the potential payment credentials, use either text-based pattern matching for payment keys or file format filtering for other credential files. The scanner also performs the black box scanning on the merchant server here. According to our study, many merchant apps hard-code the values of their notified URLs. Thus, our tool can extract them out from their APKs. Then our tool or the scanner can construct and pop the URLs and points that may point to the credential files that exposed in the merchant servers. Finally, the detector module validates the potential payment credentials. As the scanner only performs pattern matching on payment keys and overlooks other context information, some output from the scanner is false positive or noise, which is caused by some stored data, such as system logs, because some developers may back up their home server code on GitHub. Thus, a machine learning-based classifier to distinguish configuration files from stored files to speed up the validation and our testing. Also, some payment keys are generated by the cashier, and these keys may have similar channel entropy, so that we use an entropy filter to remove the false positives. On the other hand, the credential files, such as client certificates in Cashier 2 and the Android signing keys, are password protected, and we use different strategies to crack them locally. For example, the suggested password for PFX certificates in Cashier 3 is a 6-digit, so that we use Jailbreaker to brute force them offline, while the success rate is over 99%. In contrast, the password for the Android signing key is user-defined without any guideline, so that the detector will go back to the original GET repository and try to unlock the Android signing key file with all the string values inside. Such an approach gives a success rate of over 60%. Meanwhile, the activeness of a given Android signing key can be checked by the detector here. To be specific, the tool will try to find the Android package name from the original GET repository, download the associated APK, and compare their hash values to complete the checking. In short, we have detected over 400 active Android signing keys so far. Finally, we use an online approach to validate the refined payment credentials. The detector will use the suspected payment credentials to prepare a malformed order query request to the cashier, which will definitely trigger some error code. For example, illegal sign in the example means that the payment key is not correct, while tried not accessed indicates that the key is valid, based on the difference in the returned error code from the cashier server. PKMiner can then validate the payment credentials. To avoid affecting the normal protection of the cashier, we control the interval between two requests to 2 seconds. Overall, it takes PKMiner around 300 seconds to test each input. Then comes the test results. In summary, about 20,000 unique payment credentials have been detected from these 3 leaking sources, including public GET repositories, Android APK, and merchant servers. In these 4 studied caches, in terms of leaking sources, most payment credentials are detected from public GitHub and Android APK. On the other hand, most credential leaks happen in cache 2, which is consistent with its widespread integration in mobile apps. Now, let's discuss the results from 3 leaking sources, one by one here. In terms of the public GET repositories, we have tested around 140,000 input from various sources, while 10.3% of them leak at least one valid payment credential. Meanwhile, 7.8% of the payment credentials only accessed in old GET commits. That indicates that some developers have noticed the leak issue, but fixed it wrongly by pushing new GET commits instead of updating their payment credentials. On average, it takes 51 days for the developers to take such wrong fixings. Besides, among the results, we find 712 payment credentials that are related to iOS apps. Another interesting finding is that most of the public GET repositories belong to some outsourcing companies. These companies are only responsible for development but not maintenance, so that they may not care much about the security issue. In the case of Android APKs, around 5,000 payment keys are detected from over 7,000 APKs. Besides, 3 apps embed the client certificates in cache 2, while these merchant apps use these certificates to request the cache server. For some management interfaces, such as refunding, also 31.9% of these keys only accessed in old versions. There are 2 other interesting findings when we studied the result from Android APK. First, we studied the leaking locations of these payment credentials and find that around 2,000 keys are from the same location or Android activity. This activity actually belongs to the official front-end demo project provided by one certain cacher. Although this cacher claims that the project is only for demo use and gives a strong warning about a leak issue in this demo, many merchant apps still reuse it for their own payment service. Meanwhile, we find one certain payment key appearing in hundreds of merchant apps, which actually belongs to a payment aggregator. The so-called payment aggregator works as the proxy between the real merchant server and the cacher server. However, this payment aggregator leaks its key in the front-end SDK and affects all the written merchant app. Now let's turn to the results from merchant servers. Our tool has recovered around 800 notified URLs or merchant servers from Android APKs. The other apps do not embed their notified URL, while its value is still visible in runtime. Notably, 7% of these tested servers are vulnerable, meaning that they use the flawed backend SDK provided by the cachers and do not forbid the access to their credential files, as the backend SDKs are the same for either Android or iOS apps. The iOS apps can make the same mistake, and we have found such cases manually in the collected GitHub repositories. We have reported our findings to the related cachers. Besides, after our initial testing, we sent 2 cachers over 3,000 leaked keys. According to the cachers, they would alert and urge the related merchants to change their payment keys. Meanwhile, we conduct regular monitoring on the related GitHub repositories to study the responses from these leaking merchants. To sum up, there are 5 types of responses by the merchants. First, some merchants choose to update their payment key, which is the correct fixing. However, some merchants choose to hide or remove their GitHub repositories, while the other merchants tend to remove the related Git commits or push new Git commits instead. On the other hand, many leaking merchants have not made any responses so far. The table below shows the situation when we retested these leaking repositories 12 months after our first report. Unfortunately, as we can see, only 16% of the reported key had been updated by that time, while the others were still valid. Now I will talk about how to find the leaking merchant apps that are related to the detected payment credentials. Some credentials are got from the server code in GitHub repositories so that we cannot find the associated merchant apps directly. Thus, we developed a 4-in-3 approach for this target. First, some payment credentials also work for websites so that we can craft the corresponding payment request and send it to the cashier server. Then the desired app information will just appear in the response from the cashier server. We automate this approach and have identified around 1,500 apps. On the other hand, the client certificates are usually leaked along with the related payment keys in Cashier 2. Besides, the API information is available after we unlock the client certificates. We automate this approach and have identified around 3,000 leaking merchant apps. The last approach is to hook the cashier app. We find when certain cashier app will extract the information of merchant app from its server in each payment. As a result, we can hook such a function in the cashier app to get the identity of the leaking merchant app. We have completed the proof of concept for this approach, but have not automated it so far. Finally, I will give some suggestions in fixing the payment credential leaks. To conclude this talk, first, the cashier should warn their merchants about the serious consequences of payment credential leaks. Next, the cashiers should timely fix their insecure implementations, such as the flawed backend SDKs and misleading front-end demo projects. Also, the cashiers should conduct proactive scanning on the leaked credentials and revoke them in time. While to the merchants, they should periodically update their credentials, which may be leaked in some unknown but public places. We have released a white paper where you may find more details. And that is the end of my presentation. Thank you.